Okay, so now in 11.1 we went over sequences in general. In 11.2 we went over series. Only series that when they converge we can actually find their sum, like geometric series and telescoping series. Okay, they were easy to maneuver with. Now from here on things are not as easy, but it's not going to be difficult yet. So we're going to talk about the integral test. Although the title says the integral test and estimates of sums, we're not going to go about estimates. We're just going to do the integral test. So in the previous section, like I said, we could actually find the exact sum of the series, whether it's geometric or it's telescoping. Okay, those we can actually say they converge to 5, or they converge to 1, or they diverge. In this section and the next few sections, we'll only talk about convergence tests without being able to find the exact sum. So we're going to say this series converges or this series diverges. What's the sum? We can do an estimate, but we're not going to worry about the estimate. Okay? So what is the integral test? And that does involve not just integrals, it involves improper integrals. All right, so if function f is positive, so it has to be positive, okay, and continuous as always, and decreasing. So meaning if you find the first derivative has to be negative for x greater or equal to 1, okay, and if an, so we're matching the sequence with the function, then the series of an from n equal 1 to infinity and the improper integral from 1 to infinity of f of x dx either both converge or both diverge. The beauty of this is, since we know how to do improper integrals easily, we can find the integral of that sequence using a function. If that integral converges to a number, then we say the sequence converges. If that, but it doesn't converge to that number, it just converges. If that diverges, then we say, or equals infinity, then we say that diverges. Now it doesn't have to be from 1 to infinity. You could start here at 3, but then you do 3. You could start here at 5, then you do 5. Okay? Now the proof isn't too bad, so you can look at the textbook for the proof if you're interested. And so you don't have to start at n equal 1, they have to match, and also the function doesn't have to always be decreasing. It has to be decreasing for all n. It doesn't have to be greater or equal to 1. It could be greater or equal to 5 or greater or equal to 6 for some positive n, okay? So it has to be, after a few terms, it has to be decreasing steadily. But it doesn't have to be. The first, second, third, fourth term maybe don't have to act that way. But after a specific term, then they have to be decreasing. Okay. So use the integral test to test for convergence. Sum n is 1 to infinity 1 over n. Well, we know this is n to the p, where p is 1. We know it diverges, but how do we do that? Well, this is, so f of x would be in this case 1 over x. This is continuous for x greater or equal to 1. That's what matters, right? It's not continuous at 0, but who cares? And it's decreasing, and it's positive. So it satisfies the integral test. So we do the integral 1 to infinity 1 over x dx. It's ln of x, which is ln of, limit as t goes to infinity 1 to t 1 over x dx. We're going to do t limit as t goes to infinity, which would give me ln of infinity, which is infinity. So the integral diverges, so the series diverges. Okay. Also, we know this one is convergent. It's a p series with p greater than 1. But let's show that using integral. Again, this is a function that's continuous for x greater or equal to 1, positive and decreasing. So the integral from 1 to infinity 1 over x squared dx equals limit as b goes to infinity, or t, it doesn't matter, 1 to b 1 over x squared dx, which the limit as b goes to infinity negative 1 over x. So the limit as b goes to infinity negative 1 over b plus 1, which is 0 plus 1, which is 1. So the integral equals 1, so, or converges to 1. So the series, we just say that the series converges. Does it converge to 1? We don't know. We just say converges, okay? But it may or may not be convergent to 1. We cannot make that conclusion. Alright, sigma k equal 3. So you can see we don't have to start at 1. ln of k over k. Again, f of x in this case is ln of x over x. You can check for x greater or equal to 3, right? You can check that this is positive, it's decreasing, and it's continuous. So the integral from 3 to infinity ln of x over x dx, which is the limit as b goes to infinity, 3 to b ln of x over x dx. We can use substitution. U equals ln of x, so du is 1 over x dx. So this would be the integral of u du, which is u squared over 2, which is ln x squared 1/2, 3 to b, limit as b goes to infinity. It's 1/2 ln of b squared minus 1/2 ln of 3 squared. ln of infinity, that's infinity minus a number is infinity. The integral diverges, so does the series. So the series diverges using the integral test. All right. So number 10, page 758. Sum n equals 1 to infinity, tangent inverse n over 1 plus n squared. It says use the integral test to determine whether the series is convergent or divergent. So they're telling us to use the integral test. The integral, so they're assuming the function is positive, continuous, and decreasing. Okay. So we're going to do the integral from 1 to infinity, tangent inverse x, or 1 plus x squared dx, which is the limit as b goes to infinity, 1 to b, tangent inverse x over 1 plus x squared dx. So if we use the substitution, u equals tangent inverse x, so du is 1 over 1 plus x squared dx. So that integral is going to be integral of u du, which is 1/2 u squared. We'll put the integral in a second. So it's 1/2 tangent inverse x squared from 1 to b, and then limit as b goes to infinity. So let's plug limits in first. Half tangent inverse b square minus half tangent inverse 1 square. So tangent inverse infinity square, that's going to be pi over 2, right? Tangent pi over 2 is infinity, and then tangent inverse 1 is pi over 4. So be pi square over 4 times 1/2 is over 8. Pi square over 16 times 1/2 is pi square over 32, which would be 3 pi square over 32. So the integral converges to this number, so the series converges. We don't know to which number, we don't care, it just converges. Okay. So I mentioned, P series earlier. Let's talk about those, harmonic and P series. Sigma 1 over n to the p, n equals 1 to infinity is 1 over 1 to the p, 2 to the p plus 1 over 3 to the p plus 1 over 4. This is called a P series. Okay, a power of P, a P series. This is converges if P is greater than 1 and diverges if P is less or equal to 1, between 0 and 1, okay, including 1. If you use the integral test, the proof is easy, okay? Okay, see the book, it's very easy proof. So now, by just looking at the series, if we're looking only at sum 1 over n, 1 to infinity, where the power is 1, this is harmonic series. So if you see harmonic series, it's a P series where P is 1, okay? So now, right away, if I say, what is this? N to the 3 halves. You say converges, it's a P series, P greater than 1, it converges because of that. If I say sum 1 over n to the 1 half, you say diverges, it's a P series with P between 0 and 1, okay? Number 16, page 758. 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4 plus 1 over 5 root 5 plus, and it says determine whether the series is convergent or divergent. So we can write this as sum 1 to infinity 1 over n root n, because this is 1 root 1. So which is sum from 1 to infinity 1 over n to the 3 halves. So it's a P series. P is 3 halves greater than 1. So series converges. Okay. Here's another example. What if I have 1 plus 1 over cube root of 4 plus 1 over cube root of 9, 1 over cube root of 16, 1 over cube root of 25 plus. So we can write this is cube root of 1, which is 1, so we can write this n equal 1 to infinity cube root of n square, right? 1 square, 2 square, 3 square, 4 square, 5 square, which is, we can write it as a P series where P is 2/3, P series, P is 2/3, which is between 0 and 1, greater than 0. So we say the series diverges. Okay, say that the series diverges. Okay, so number 34, page 759. It says find the values of P for which the series, for what values of P this series converges. So it's not a P series because it has an n up there, okay? So so P could be positive, could be negative. So let's consider those cases. So if P is less or equal to 0, okay, then AN equals ln over n to the p, and the limit, we're going to do the test for divergence, ln over np, because p is negative, you move it up, it becomes positive, times ln of infinity, so infinity times infinity, which would be infinity, and we say the series diverges by the nth term test for divergence. If the limit of an does not equal 0, then the series diverges. Okay. Now if p is like, what if p is greater than 0? So now we're gonna do f of x equals ln of x over x to the p. F of n equals an, and I showed in the notes that, you know, I did the first derivative. You can check it out. F prime of x is less than 0 if x is greater than e to the 1 over p. So it's essentially decreasing as long as greater than n. Okay, it's decreasing, it's positive, and it's continuous. So we can use the integral test. And here's the integral test. So integral from 1 to infinity ln of x over x to the p dx, which by definition is limit as b goes to infinity 1 to b ln of x to the p dx. We're going to use integration by parts because it doesn't work other, you know, that's what I did. So using integration by parts, by letting du equals ln of x, dv is x to the negative p dx. So du 1 over x dx, and v, the integral of that, which is x to the negative p plus 1 over negative p plus 1. So this would be u times v, remember integration by part, minus integral of v du, u times v, which is times x to the 1 minus p over 1 minus p minus integral of v, x to the 1 minus p over 1 minus p du is 1 over x dx. I'll bring the limit back. Just let's just work this out first. So this would be ln of x to the 1 minus p over 1 minus p minus, if you do the 1 minus p minus 1, it's gonna be negative p. So it's 1 over 1 minus p, bring that out, x to the negative p plus 1 over negative p plus 1. So you're going to have 1 minus p squared at the bottom. So what I did, I factored out 1 over 1 minus p. This is 1 minus p squared. So if I took out 1 over 1 minus p squared, and that's going to be ln of x times x to the 1 minus p times 1 minus p minus x to the 1 minus p. So we're going to do limit as t goes to infinity 1 to t. So if you put that in there, you're going to get limit t goes to infinity ln of t to the 1 minus p times 1 minus p minus 1 minus p minus, if you put a 1 in there, that's a 0 and that's 1. And so we're doing limit as t goes to infinity, t to the 1 minus p. So remember, if p here is greater than 0, right? If p is greater than 0, so it could be greater than, could be 1/2, which is no good. We want p to be greater than 1. So if p is greater than 1, that means 1 minus p is going to be negative. So we move this to the bottom. And then ln of t over t to any power would go to 0. And that's also going to go to 0. So it's going to converge if P is greater than 1. It's going to converge. So this series, and it diverges otherwise. Okay, so this series is going to converge for P greater than 1. Alright, it's not straightforward, but look at it. And that ends 11, 2.